Okay, good morning, everybody. Welcome back to this CST 131 lecture. Today is the early morning lecture. It's early even for Malaysians. If you are joining in from countries in the western side from Malaysia, you will be even early this morning. So we thank you for taking the effort to join us this early morning. Okay, so where we left off on Tuesday, we were basically talking about the structure and function. Okay, so in the slides leading up to where we left off, we were basically trying to define what the structure is. So basically, the structure are the components that are interrelated. All right, and then for the function is basically how these components of the structure function. Okay, how they operate and how they process and do their job. So that's basically the difference between structure and function. Okay, so to continue the lecture, to continue the slide deck, let's discuss a little bit more in detail what constitutes the function of the computer, or the function of the various structural parts of the computer. Okay, so basically all computers do these four main functions. Okay, so if you can see on the slide, the first one is data processing. Okay, that's very important. So processing of data. The other one is storage of data. Okay, and the third one here is the movement of the data. And finally, the fourth one here is the control of the data. Okay, or rather control how it moves and stuff like that. So, so for a functional view, you will notice that there are four main functions here. So you can see at the top here, there is the data movement, and then connected to the control mechanism, and then followed by the storage facility a little bit to the bottom left, and then the processing facility here to the bottom right. So we see how the four functional the four functions are somehow interrelated together. But what are the various operations that are more important? So, like for example, the first one is the data movement, right? We're talking about the data movement. So the control unit here, the control mechanism here, coordinates the movement. All right. So and then here it shows that how the data is moved from one part to another part of the component. So movement is one of them. Okay, and facilitated by the control mechanism. Okay. Next is the storage operation, the storage function. So if you notice, what do you store? Definitely you store data or something like that. And this data has to be moved from somewhere before it is stored. So likewise, if you see in this particular diagram, you see that data is moved to the storage. Okay, so there is some data movement which eventually ends up in the storage mechanism. And if you notice here also, the control mechanism facilitates this movement of data, okay, and finally stored in the storage. Okay, so that's the second one. The first one was movement. The second one is storage. Now the third one here is processing. Okay, processing, and processing usually happens from the storage as well as to the storage. All right. So if you notice, very often, if you think about the computer that we have, the RAM is so important, right? We're talking about the RAM. Why the RAM is so important is because a lot of the processing is done from the RAM. That means the data is brought in from the RAM in order to do the processing. Okay. So therefore, if you see in this diagram, the processing happens to and from the storage. Okay. So from the storage, it is again facilitated by the control mechanism, and then the processing happens. Okay, and after the processing has finished, well, the output needs to go somewhere, and then of course, it goes back to the storage. Okay, so that's how the processing operation happens. Okay, now the processing can also happen from storage to the data I/O part. I mean the input and output part. So let's say, for example, after the processor has processed some form of data, where did the data come from? It came from storage, right? And then maybe that data needs to be printed, or that data needs to be shown on the monitor, or that data needs to be conveyed to and from the mouse or to some other device. Okay, so therefore the processing happens in order to bring the data to an output peripheral or output device or output whatever. So the movement here, or rather the process that is going on here is the processing is from data from the storage, and after that move to the I/O in order for it to be displayed or printed or whatever. All right. So if you notice, yes, there are 4 slides I've shown here: processing to and from storage to I/O, processing to and from the storage itself, and of course the data movement. Now, what I didn't cover here is the control. Okay, I didn't cover. There's no diagram for the control, and if you notice, based on this 4 diagrams alone, the control basically facilitates. I use the word facilitate, but basically it handles all the signals and movement to and from the I/O, which is the movement, the storage, which is the RAM and so on and so forth, and the processing, which is the processor. Okay, so although there's no slide for control, but I hope you can appreciate that the control facilitates everything that you actually see on the slides. Okay. Now, a very quick question now. Based on these 4 functions, processing, storage, movement, and control, which is the most important? Which do you think is the most important? Okay. Maybe you can just quickly put in the chat box, right? I see some responses coming in. Okay, just let me see from the top of the list. Okay. Control, all of them. Control, processing, control, all of them. Control. Okay, quite a number. Majority says control, all of them. Control or processing. Okay. Ikmal said maybe control, maybe processing. Okay. All absolutely control. Okay, absolutely control. Control. Processing. Okay. Some of you think it's processing. All right. Control or data movement. Okay. Some of you think that it's probably even data movement. All right. Okay. So do you think there's a right and a wrong answer? Okay. Let's see. Which do you think is the busiest? Okay. Which do you think is the busiest among the 4 functions? Okay. Again, maybe you can share in the chat. Control again, processing, control, processing, control, processing. Some of you now changed your mind. Now it's control now. Okay, keep it coming. Okay. Control processing. Okay, right, good. So now I think some of you have changed your mind to control. All right.
Sir, you mute your mouth, sir. You mute your mic, sir.
Oh, sorry, forgot. So based on the so now the question now here is which is the most important? So I think from a lot of the responses in your chat, I would now assume that many of you would think that the control is the most important. Okay. Now why is this so? If you see the diagram, if you see the diagrams, whether it is actually I/O based or data movement based or storage or processing, okay, and this processing can come from the storage and or to the I/O. All of them involve the control. Okay, so you might be able to appreciate now that the control is maybe the most important, maybe the most the most busy or the busiest. Okay, but some of you think that it is the processing, okay, or the processor, which is also important because the processing, without the processing, you can't get the actual output. Although the control facilitates, but the control cannot produce the output, right? But the processing is the one that produces the output, which is the thing that we want actually. Okay, so well, which is the most important? Although you might think the control is the most important, maybe processing is also very important, although it is not the busiest. Okay, now again, I'm not going to say that there's a right answer or wrong answer, but but I think maybe some of my friends think that all also are important, right? Yeah. So I mean, I'm not saying that's right or wrong, but it's something for us to discuss. Uh, which component or which function plays an important role in making a computer do what it does best. Okay, right. Okay, good. Thanks for all your responses in the chat box. Appreciate your enthusiasm. Yeah. Now let's move on to the structure now. Just now we talked about the four functions. Four functions. The functions are processing, control, storage, and movement, data movement. So now let's talk about the structure now. Now, basically, in terms of the structure, there are four main components. Four main components. Okay, the first one here is the CPU, the Central Processing Unit, also called the processor. Okay. Now, this one basically it controls all the operations and performs the processing. Okay. You also have main memory. Basically, it stores the data. Now, main memory is the more so-called general term. Some people will call it RAM, okay, the random access memory. But of course, main memory, yeah, again, it's a very umbrella term lah. Even if you don't call it main memory, some people call it memory in general. But of course, memory again is a very very high level thing, which also includes the cache and all that. But very often, main memory, a lot of people refer it to the RAM. Okay. Now, the third component here is I/O, which stands for input output. Okay, and this is responsible for moving data lah. Okay, between the computer and the external environment. External means outside of the processor lah. Okay, that means it could be all the interconnections on the motherboard and also the I/O module which connects to the USB, the monitor and printers and so on and so forth. Okay. And the fourth one here is the system interconnection. This one is the connections between the processor and all the other important components such as memory, I/O, and so on and so forth. Now, this one again is usually the motherboard kind of connections, right? Okay, let's take a look at a schematic view of it all. So let's say now we have the computer. Okay, we always think that, oh, but whatever is in that box is the computer, right? Rightly so lah. So that computer is connected to devices. So we see at the top here are those are the peripherals, your mouse, your keyboard, your monitor, and all that. So and then you also have communication lines, which it could be your network and all that stuff. Okay, so the computer. If you look inside the computer, then we have a few things. Now you can imagine when you open up the computer, you will see a motherboard. Okay, now after I'll show you a diagram. I know that perhaps 2/3 of you have not opened the computer to see what is inside and touch the components and all that. But you can imagine you open the cover, you will see the motherboard, but they are basically organized into four main important sections, right? So you have the CPU, which is the central processing unit, the main memory, the input output, and the system interconnection. Okay, so very much the four items that we see on the screen now. Okay, so now let's look a little bit deeper now. Okay, so this is the schematic view. So you see the PC from the outside. You open up the cover, and you will see all these type of things. So some of it is the processor, some of it is the memory, some of it is the connections, and some of it is the I/O. Okay, but if you look a little bit more into detail, so we can then label it lah. Okay, so if you notice that towards the right, the little square there, that is the processor. Okay, there are a few I/O related components such as all these PCI slots, the I/O panel at the end, all the PCI express slots, the SATA connectors. Those are the I/Os. Okay. Now, where is the main memory? The main memory usually refers to the RAM slots, which is the yellow and orange slots here. Okay. And then the interconnections are all the little very, very fine lines that you see all over the motherboard. Okay, so that means these four little blue squares, four little blue circles on the right side of the screen are then mapped to some of these components on the motherboard. Okay, so this is a desktop kind of motherboard. This is another example of a desktop motherboard. Again, the big square in the middle is the processor. The two long black squares here is the RAM. Then the I/O are all over the place. You have some slots here and also all the ports, right? Those are the I/O. And then all the interconnections, which are all the very, very fine lines on the motherboard. For the laptop, it is pretty much the same, but instead of some vertically connected components, a lot of the components on the laptop are horizontal. Okay, so like for example, in the desktop, all the RAMs are connected, perpendicular to the motherboard. But some of the RAMs for the laptop, they're connected sideways, so to save space, so that the laptop doesn't get too thick, right? All right, so those are the insights of the computer a little bit for those who have not gone into the computer. So let's look a little bit deeper into the CPU. Okay, now earlier we saw the computer is then made up of the CPU, memory, interconnection, and the I/O. Now let's look at the processor, and then we blow it up a little bit. Okay. So the CPU, when we blow it up, so inside the CPU itself, you have various components. You have the registers, you have the arithmetic and logic unit. Sorry, the spelling error there. Let me correct this logic. Okay, so you have the arithmetic and logic unit. You also have the control unit. Okay, and then we have the internal CPU interconnection. Also, if you notice, from this diagram, there is no control component, right? We have learned that there is processing, there is I/O, there is main memory. We also learned the one of the functions is the control, right? But the control is not shown in this diagram. But control is actually in the CPU itself. Okay, there's a control unit in the CPU. Okay. Now, let's blow up the control unit. Okay, let's blow up the control unit to see what is inside. In the control unit, there is a sequencing logic. Sorry, again, there's a little spelling error here. Okay, so there's the sequencing logic. You also have registers that are dedicated to the control unit. Okay, and of course, there is some memory for the control unit itself. Okay, so these are some of the internal components of the computer in general. Sorry?
The control memory in the control unit, is it the cache or it's another thing?
Oh, it's another thing itself. It's a dedicated memory for the control unit. Okay, the cache is actually more for the processor. The cache is more for the processor's processing, but the control unit has its own control memory. We will learn control memory, I think, when we learn the CPU later. I think Dr. Mamit will be covering that later. Yeah.
You are going to dig deep in every single bit of these things.
Sorry again?
You are going to dig deep in every single thing of these categories.
Yes. It will be covered in the. Yeah, eventually when we do the topic on CPU, I think it's covered by Dr. Mamit later. She will discuss a bit about the control memory and so on. Because there are various ways to implement the control unit. And one of the ways is a software version of a control unit. And therefore, for a software version to be successful, you need some kind of memory. Okay. The other way of implementing the control unit is the hardwired control unit, which I think I won't talk about it now. We will discuss that later in the other topics. Okay.
Okay.
Okay. Thanks for your question. Right. So if you notice, I've shown you two main structures. Okay, I have shown you two main structures. The computer, which has the CPU, main memory, I/O, and the system interconnection. Correct? If you remember this one. Yeah. So the four main components of the four main structure in the computer, you have these four items, which is also shown in this diagram. Okay. Now then, you also have this one on the right side of this slide. You have the central processing unit, the CPU itself. Okay. Now the CPU itself has the arithmetic and logic unit, the registers, control unit, and the internal CPU interconnection. Okay, it is shown in this slide. Yeah, this one. So the CPU, inside the CPU, when you blow it up, you have the ALU, registers, interconnection, and control unit, right? So, what can you notice from all these four components? You see, the computer has these four components, and the CPU itself has these four components. Now, what can you notice from all these four components? Maybe you can share in the chat box. Are there any similarities, or are they very different, or what do you notice? You know, the computer's four components and the CPU's four components. What can you notice?
ソーレディ・ベローナ誓いの剣を
アクアマグナ
バイス・フリューゲル
Okay, let's go through the chat box. CPU is basically a miniature computer by itself. Oh yes, that's true.
うちの頼んだで
CPU is a mini computer. CPU itself is a computer. The ALU unit is similar, I
お
think.
尻ペンペンや
They have similarities in their functions. Okay, good. Both have interconnections. Everything is divided into 4 components. ALU is different. Okay, ALU is different. Needs an interconnection. Both have interconnection. Both internet is kind of similar. Okay, it's kind of similar. Both have the same concept for each of the 4 components. Okay, yes, all right. All the computer most contain CPU. Okay, all right. All contains the CPU. Both have interconnection related in each of the components. CPU is divided into 4, same as the computer. Okay. I will have to just randomly scan through. Both are complex structure and have 4 components. Okay, CPU is the brain. CPU is like the function that explains the main unit of the computer, similar structure, interconnection. CPU is the heart of the computer. Okay, very good. All those are all your responses are very good.
見ましたね
But I'm attracted to some of your comments that state that they are similar in nature. Okay, similar functions. If you notice that, if you look at the computer, the brain of the computer that does the processing is the CPU. Okay. If you look at the CPU itself, the brain of the CPU, the one that does the processing, is actually the ALU. Okay, because what does the computer do? It does calculations, it does logical, functions and all that. So the processor of the CPU is actually the processor of the processor, something like that. The processor of the processor is the ALU. Okay, now. On the computer side, we have the main memory, the main memory, which is the RAM. But inside the CPU, there's no RAM, but it also has some memory. Okay, and this memory is in the form of registers. Okay, registers. We call it differently. Why? Is because registers are very, very, very fast memory. Okay, it's faster than the RAM. All right. So, but yeah, it's a form of memory itself. Okay. Next, we have let's talk about the system interconnection first. Just like the computer has all the various functions and they are interconnected together. Okay. CPU connected to memory, memory connected to IO connected to blah, blah, blah. Okay. So you have all the components and they're interconnected. Inside the processor also, there are interconnections, which means the ALU is connected to the register is connected to the control unit, and they're all interconnected. So inside the CPU, there is also some form of interconnection. All right. The main difference here maybe is between the IO and the control unit. Their functions are not so similar, but we can view that the control unit handles the movement. Okay. And of course, in the computer, where does the movement go? The movement goes to the I/O to some extent, not in all cases, but I/O is related to movement of data, especially towards to the outside of the CPU or to the outside of the computer, like the mouse, monitor, and so on. So yeah, there are some similarities also between the I/O and control unit, but not so clear, okay. Question in the chat. Let me see. Are registers like cache memory? Okay. Now, cache memory is still on the okay. Let me. There is some cache in the processor. Okay. Now, in older machines, a lot of the cache are on the motherboard. Okay, but in most modern processors, there are also cache in the CPU itself. Okay, but CPU, but for the CPU, cache is still considered slightly slightly on the outside, which means you have RAM at the very high level, then you have cache, and then you have registers. Registers are even closer to the ALU or closer to the processing itself, okay, which makes it even faster. So that means the ALU will look for data from the registers first. And when it's not in the register, then it looks from the cache. When it's not in the cache, then it looks from the main memory. Okay, so that's how the hierarchy of searching goes. Okay, so registers are not the cache. Okay, it is even closer to the processing in the ALU. Okay. Probably more similar to RAM. No, the register, it's not the RAM. Okay, it's in the processor itself. Store temporary data, yes. So ALU, the registers store data for the usage of the ALU. So the ALU does not retrieve data directly from the RAM, or ALU doesn't use data from the cache. It uses whatever is in the registers first. Okay. What about CPUs that have integrated graphics? So so if the CPU has some integrated graphics processor, so that handles the graphical processing. So it is something like an ALU, but the ALU dedicated for graphical processing, like 3D movements and all the stuff like that. Okay. Righto. Any questions so far? Aside from those in the chat, after you have heard some of the stuff, then do you have any questions for the function and structure? No? Okay, so let's proceed. Oh, doctor, may I ask a question? Yeah, sure. You can either ask verbally or you can type it in the chat. You did mention that the CPU processes data from the RAM. Okay, yes. Can the processing unit directly process data from permanent storage device like hard disk, or does it process data from the RAM? Okay, that's why there's actually a hierarchy. Later, when Dr. Mamit introduces the topic on memory, she will also introduce to you how the hierarchy of memory is organized. Okay, so just now I told you, I shared with you, from the ALU itself, the ALU looks for the registers first. Then from the registers, they look for it in the internal cache nearest the processor. Then if there's any cache on the motherboard, then that goes to the cache on the motherboard. So notice that cache, you have level 1, level 2, all this kind of stuff. Then after the cache, then comes the RAM, the main memory. Then after the RAM, then only comes the external storage, like your hard disk or your solid state disk, or your CD-ROM, if any of you are still using CD-ROM, or your USB drive or whatever. So the hard disk and CD-ROMs and your USB drive, those are all considered external storage, which is again very far away from the processor. So on a normal basis, the processor does not deal directly with all the external storage. Okay, the processor will deal with the RAM first. Okay, and of course, but there are a lot of things in between. So it looks for it in the registers first and So if you notice, when you want to run a particular application, let's say you want to run Microsoft Word, or you launch your Google Chrome, or whatever application that you want to run, you will notice that the CPU, the hard disk light will blink, right? Now, when the hard disk light blinks, means that it is reading data from the hard disk, and it's brought into the RAM first. Okay, chunks of it are brought into the RAM, and then chunks of it are being put onto the cache, and then chunks of it are being transferred to the registers, and then only the processor handles the processing directly from the register. Okay, so it's something like that, but I won't go into detail because it will be covered later in the topic of memory. Okay, so I hope that covers the question regarding does the CPU deal directly with the hard disk? Okay, let's continue. So now we have done with architecture and the family and the organization. We also have clear structure and function. Okay, now let's talk about other things. Let's talk about multi-core processors. Okay, a lot of modern computers nowadays, you hear that they are multi-core, dual core, quad core, 16 core, the various number of cores. But let's talk about some terminology first. Okay, what is the CPU? CPU basically fetches and executes all the instructions. Okay, it is actually basically the processor. Okay, it is the processor with a single processing unit. So let's say, for example, if your processor has only one processing unit or one ALU, well, that is the processor already. Okay, and that is the CPU also. So CPU, processor, processing unit, all those are the same if everything is just single. Okay, so that means if you have one processing unit, in that processor, that is also the CPU. Okay? So if you have a single core machine, okay, let's put it this way. If you have a single core machine, that is the processor, that is the CPU also. Okay, all right. So that is the CPU. Now, what is the core here? The core is the one that is the doing the processing. Okay, it is an individual processing unit on the processor. So which means your processor might have many processing units. Okay, maybe like maybe many ALUs or something like that. Okay, right? So that is referred to as the core. Okay. Now, what is this thing called the processor? Again, the processor is a very general term. So the processor might have one or more cores. Okay, like I was mentioning to you earlier when we talk about this CPU thingy. So if you have just one core, that one core machine is also your CPU. That one core machine is also your processor. It is just a general term. Okay. Yeah. So this diagram maybe will explain a bit better. So the top of the diagram here, you can see is the motherboard. Okay, the motherboard with all the maybe the memory slots, the I/O slots or whatever, and then you have that square thing there, which is the processor. Okay. Now, if you expand that processor, you will see the processor chip with all the smaller components. Okay, so on the processor chip itself, you have probably some cache. Okay, as I was mentioning to you, some cache are actually on the processor. So you have some cache, and then maybe you have all your registers and blah blah blah, which is also related to the core as well. Some of the registers are inside the core. So if you notice in this particular diagram, you have 1, 2, 3, 4, 5, 6, 7, 8 cores. Okay, there are 8 cores, and if you open up each core, then you notice that the core contains the ALU, even lower level caches, and I will assume some memory as well. Okay, right? So so if you can imagine, the ALU itself is actually a component in a core. So the core will have its own memory, okay, a very low level memory. The core would have its own ALU. Okay, so that is considered one core, and many of these cores make up the processor. Okay, so I hope this explains a little bit what's the difference between a processor, a CPU, and the core. Okay. Okay, what are threads? Okay, now threads are basically how the processor splits the data stream into different processing so that they can be done simultaneously. Okay, so likewise, if you have many cores, it will only make sense that all these cores can work together. Okay, but if your application or your data cannot be split into multiple streams, then having all these multiple cores does not work. Okay, for example, if you go to the highways in Malaysia, you have many toll lanes, right? Now, if you have only one car, it doesn't make sense to have so many lanes for you to go and pay your toll, isn't it? So you can imagine having these multiple cores here will only make sense if you have many cars coming together, and all these cars can go into different lanes. Okay, yeah, so something like that. So the threads here refers to the ability of many cars to be processed at the same time. But if for some reason, let's say for example, when companies want to transport cars, they use this long trailer with many cars inside. Okay, now all these cars cannot go into separate lanes. they all have to go into one lane. Why? Because they're all transported by this big trailer. So in those cases, having multiple cores doesn't make sense. Why? Because those cars are stuck on the same trailer. Okay, they cannot separate and go into different lanes. Okay, so that's the analogy I'm trying to illustrate to you lah. So having the threads means that your data is able to be distributed into different processing channels, and then they can go into different cores lah. Okay. All right. More cores means more performance. That's why again, not necessary so. If your application or your data cannot be separated into the different cores for processing, you won't get any improvement in performance. Okay. Right. I think later when we talk about the CPU, you will also face some of these issues because later we will talk about this thing called pipelining, and there's also this issue about having different stages being processed at the same time, and that will result in a speed up. But I think I won't discuss it now, okay? But later we will later I think Dr. Mamit will introduce this concept whereby how can how can how can instructions be stacked together so that they can be processed simultaneously. Okay. Okay. So that concludes some brief introduction about multi-core. Okay. We will then go into another section called computer evolution and performance. Okay. You guys want a short break? If you want a short break, just yes. Okay, a short break. I will give you a 5-minute break. Okay. Okay. Now let's not make five. Let's round up the figure. We resume at 8:55. Okay, that makes it maybe a 7-minute break or so. Okay, we resume at 8:55. Okay, I'll see you later. Thanks.
Can you speak French? I'm assuming that's what you mean when you say baguette. Salut. Je m'appelle Gaogura. Je suis Same. Je suis shark. Nope, that's all I got. Okay. No, you're breathtaking. Fly Me to the Moon by Frank Sinatra.
みんな無事だったか。よし、陣形を整え。
Fly me to the moon, let me play among the stars. Let me see what spring is like on Jupiter and Mars. In other words, hold my hand. In other words, maybe kiss me. Fill my heart with song, let me sing forevermore. You are all I long for, all I worship and adore. In other words, please be true.
みんなでおやつ触れる相手ならごつんとお仕置きできますね。
In
そ
other
の身に刻むがよい。
Okay, I hope everyone is back. Okay, there are a couple of questions I noticed on the chat box. Some of it I won't go through because it's actually beyond the scope of the topic today, such as hyper-threading and all these things. For example, hyper-threading is just a kind of threading, and it's used by some manufacturers to call their threading in a special way. So it's sometimes a business or a marketing kind of terminologies which they use. But ultimately, threading is threading, and it is implemented in different ways. Okay. Does a control unit be present in each core in the CPU or both? Now, actually, there will be controls at different levels. Okay, but at a high level, there will be a control unit at the main processor level. Okay, but of course, in each core, they will have their own internal logic, and that internal logic is something like a control unit as well, although maybe not necessarily called a control unit. But internal to each core, there will be some logic, as I was mentioning to you, and that logic guides the control of how the data moves and all that. So yeah, some form of control is also present in the core as well. Okay. Okay, I think I shall continue. Just give me a minute. I will start the recording and then we can continue.
Let me sing forevermore. You are all I long for, all I worship and adore.
Okay, so in this next half of the lecture, we'll we'll discuss a little bit about computer evolution. Okay, some history of computers. If you don't like history lessons, hopefully this will be an interesting history lessons. A little bit about the X86 architecture, PowerPC, and the ARM processor. A little bit about cloud computing. If we get there, I'm not sure whether we can cover so much today. Otherwise, we will discuss some of this on Tuesday. and how the performance of the computer is being evaluated. Okay, so there will be some performance criteria that we can to see how computers perform basically. Yeah? Okay, just as a warm up to this second half of the lecture, what mobile phones are you using? Okay, are you using any one of these? Maybe you can quickly share in your chat box. Are you using any of these?
Sinatra.
1, 6, 3. Just kidding, eh? Okay, or maybe one of these. Yeah, maybe one of these. Yeah, I suppose that many of you will be using these kind of phones as opposed to this kind of phones, lah. Yeah, but of course there will be some of us who might be still using some of the older phones because of its reliability issues, or if there's no need for the smart functions, then of course many of these phones are very, very durable, very, very durable, and are still functioning well today. I think some people are still raving about the Nokia 3310 or something like that, which if you drop it from 2-3 floors in your building, it will still work after it drops. Okay, anyway, so many of us are actually using the more modern smartphones today. But have you asked yourself what processor is in your smartphone? Okay, so maybe just very, very quickly find out the model of your smartphone and then share in a chat box what is the processor that is inside. Huh? Okay, some of the responses are coming in. Okay, Snapdragon, ARM. Okay. What else? Qualcomm Snapdragon. I think it's the similar. A12. I assume this is the Apple one, Apple Bionic. Snapdragon, MTK, A12, A13. Okay. Qualcomm Snapdragon, Intel i5. Are you sure Intel i5 produces chips? I mean, is Intel i5 used in a mobile phone? Okay, better check on that. A14, A10, Exynos, okay, Snapdragon, A14, A13, quad-core, must be quad-core something, okay, it's either the ARM processors or one of the Apple processors or something like that. Kirin, MediaTek, Snapdragon, okay, Exynos, Kirin, and NVIDIA, okay. NVIDIA is usually the graphics processor, so SDM450 octa-core, Exynos, okay. Raspberry Pi is the small board, it's not for the mobile phones, okay. Okay, octa-core, okay. Okay, some of it will be overlapping. So some of you are using the the Android phones and all the Huawei phones and some of the popular Apple iPhones. So some of the processor will be the same. So yeah, the reason why I'm asking you all whether you know what processor you use, because later we will cover the ARM processors, and that's how it is actually related to some of the more common processors that you will see in the mobile phones. Okay, so then I hold that thought. We'll eventually come to it later in the slide deck. Okay, but first, whatever processor that you're using today, be it on the desktop computers or your laptops or your mobile phones, it all started many years ago. Okay, so the first generation out of the computers, they use vacuum tubes. All right. So if you notice on the diagram on the left, you can see the size of each vacuum tube as compared to a ballpoint pen. You see the ballpoint pen, the light blue pen there. So you have these vacuum tubes, and all these vacuum tubes are arranged in racks. Okay, we see the diagram on the picture on the right. They are arranged in racks. Okay, and all of them are interconnected together. All right. So that is how the vacuum tubes are being organized. And basically, vacuum tubes were used in the very, very first computers, such as the ENIAC. Okay, I'm sure when you were in school, you learn about, oh, what is the first computer? It is ENIAC, electronic numerical integrator and computer. So that was the first general purpose computer. General purpose means it can be used for different functions, different kinds of calculations and all that. Okay. They were first used to calculate trajectory tables. When you want to fire a cannon, it has to be at a particular angle and so that you can reach the target. So they are used to calculate those trajectory tables. So it took 3 years to build the machine. Okay, but it was actually too late to be useful in the war. So it was used to do calculations for the hydrogen bomb in 1952, I think. So so it is considered general purpose because it can be used for different purposes, different kinds of calculation. Okay. Contrary to popular belief, a lot of people think that computers are binary machines. But ENIAC was designed in such a way that it is not a true binary machine. It was actually a decimal machine. Why? Because all those vacuum tubes are arranged in sets of tens. Okay, so it represents the 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and they're all together 20 sets of them. Okay, 20 accumulators. Accumulators is like a memory, something like a memory. Okay, so it has 20 sets of memories, and each set has 10 digits. Okay, so it is not the true binary machine as most of us assume it is. Okay, ENIAC has 18,000 vacuum tubes, 30 tons. Okay, uses 140 kilowatts of power. And that is something like 30-40 air cons running at the same time. Okay, and it only does 5,000 additions per second. To a human, that is fast, okay, but by computing standards, that is considered super slow already. Alright, so this is how ENIAC looks like. All its 18,000 vacuum tubes. It's like it feels a room. Okay, it feels basically a room, and it's very, very, very hot. Supposed to be. Okay, so it covers 15,000 square feet of space with all the tubes and all the wires. And the ladies here are holding different components, different parts of the vacuum tubes. Okay, maybe it's the accumulator or something like that. So it's everything in giant sizes. Okay, yeah, this is an operator checking through the machine. Okay, now that was ENIAC. Later, von Neumann and Turing, they came up with this idea of a stored program. Okay. Now, with this stored program, that also means that we need a more systematic arrangement of components so that it can take in that program, process it, coordinate the processing, and then show it as the output. So that is how the four structural components that we learned earlier. The basis for those 4 structural components came from von Neumann's stored program concept. So we need the main memory to store the program. We need a processor, the ALU, to operate on those data. We need a control unit to interpret those instructions, and an input-output to show the result to the user. Okay, so that is the stored program concept. And the IAS machine was one of the first stored program computer. Okay, and that was the IAS is also the prototype for the modern computers today. So let's say you open up the CPU and you look at the motherboard. What do you see? You see the processor, you see the memory, you see the control, and you also see the interconnection. All right. So what you see in the present day computer very much maps to how von Neumann intended many years ago. Okay. So something like this. You see the memory, the processor, the control, and the interconnection and I/O. Right. So that is the structure of the von Neumann stored program machine. Some details about the iOS. It has 1,000. Yeah. Okay. Imagine for ENET you have only 20 accumulators, right? But for the IS machine now you have 1,000. Okay, 1,000 stored storage space. Okay, and each of that storage space is a 40-bit word. Okay, so that means you can store 40 bits, 40 bits, 40 bits, 40 bits, 40 bits, and there's 1,000 of them. Okay, and for the IS machine, it is now binary. Okay, it's no more that decimal thingy anymore. Okay, and you have a set of registers. Okay, so I was mentioning to you, for the CPU to function, it has a set of very fast memory that it uses. Okay, and these are called registers. And the IIS machine has this, memory buffer register, memory address register, and so on. A list of registers for it to function. Okay, this thing, accumulator, nearly at the bottom of the list there, you will see the word accumulator. So accumulator is a storage, okay, a very fast storage that is used by the processor. Okay. This is another diagram for the IIS machine. So again, you will see memory.
Doctor,
Yeah, sorry.
the accumulator, you mean for the IS or the modern day computers?
Even the modern day machines, you have an accumulator. Okay, so that means the processor or rather the ALU would take in inputs from the data register, and after calculating, it will store it into the accumulator. Okay, so that's how it works. Now again, this one we will cover a little bit later. We will talk about how the ALU manipulates all these registers in order to produce a result. Okay, but this one is just a very high level to introduce to you some of the basic structures of the IAS machine. Okay.
All right. Thanks.
Okay, let's move now to the more commercial computers. So the IAS machine was, the prototype, but then there were then eventually commercial machines. So the UNIVAC 1, okay, UNIVAC 1 was the first commercial machine, and it was used by the US Bureau of Census to calculate census data and stuff like that. Okay, so UNIVAC 1 was a commercial machine, and again, it's a big machine that requires a room to set up. Okay. Later, UNIVAC 2 was a faster machine with more memory and its upward compatibility, which means that older programs can be run on the newer machines. Okay. Later, there were newer models, of course, UNIVAC 1100 for scientific application and so on and so forth. Okay. Right. Then came IBM. IBM produced the punch card processing machines. Now, if you haven't seen a punch card before, you can see at the top of the screen an example of a punch card. And if you notice that all the columns are actually individual data, okay? Individual data. And there will be a reader to be able to sense where the holes are, and those will be the data values, okay? And the punch card here, every row is actually a number, okay? 1, 2, 3, 4, 5, 6, 7, and so on. So the punch card is about the size of your mobile phone, roughly this size, okay? Roughly this size. When I was a small boy, I think when I was in, I think I have not gone to school yet. I think maybe early primary school when I was, between 5 to 7 years old, 8 years old. I've seen one of these cards in one of these offices where my hometown was, and yeah, it was just about this size, okay, and it's made of cardboard, very not cardboard. It's a bit like a 100-gram paper like that, okay, a thicker version of your A4 paper, okay. So yeah, so IBM produced those punch card machines, and yeah, it's much faster lah. The punch card reader will just collect all this data, read every card, and then they produce the outputs. Okay. Okay, so just a very quick rewind, a quick revision. What is actually a vacuum tube? Maybe you can share in the chat box. What is a vacuum tube? The answer is not on the slides, but if you can just share what it does, that will be useful. Okay. So what is a vacuum tube? Okay, vacuum tube, old processor, okay, old processor, part of an old processor, okay, a light bulb, something like that. First generation CPU, not exactly a CPU, it's a part of the CPU, not a core also. Some of you think it's a core, but no, not a core. It's if you can imagine, if the core is gigantic size, then the vacuum tube is a part like core. Okay, what else? Accumulator, part of the accumulator. All right. Controls current between components. Yeah, it's some form of current control, right? First generation processor, smallest unit of the first computer. Yeah, smallest unit of the first computer. Stores a decimal unit. Yeah, it could be used for that, especially for the ENIAC machine. It represents a value within the decimal base. Yeah, that's possible as well. A switch. Yes, it's something like a switch. Switch means what? On or off. Yeah, on or off. Like a large transistor. Yes, correct. Something like a large transistor. Used for digital computation. Yes, it's part of when you connect many cubes together, then it produces a result. Okay. Right, like a switch, like a switch, like a switch. The bit of that time. Yes. So how do we store a bit? That was how the vacuum tube was functioning. Okay, because the vacuum tube allows the flow of current one way. Okay, so if the current can flow, means it's on or off. Okay, so when it's on or off means it's either 0 or 1. So when it's 0 or 1, that represents the bit representation. Okay, right? So what is a vacuum tube? Is basically a device that allows current to flow one way. Okay? Something like a transistor, as your friend pointed out. Okay, good. Very good. Thanks for sharing in the chat. Now, let's move on. Second generation of computers would then use transistors. So the first generation, they were using vacuum tubes. All right. And the second generation of computers uses transistors. Okay? So basically, transistors are much smaller, obviously. Okay, you can buy transistors from electronic components or electronic hobby shops. All right, it will look something like the things that you see in the diagram. Okay, but of course, the diagram is enlarged a little bit, but transistors can be very, very small. Okay. The size of a little Lego part or something like that. So they are very, very small, much cheaper, less heat. Okay, less heat. The vacuum tube has current going through and then it heats up. Okay, something like a light bulb, like as your friend mentioning. And it's a solid state device. It's made of silicon, right? So it's sturdy. It's hard, it's not so fragile. Imagine the vacuum tube is made of glass, so it's easily breakable and things like that. So yes, transistors, they are like a switch as well, allowing current to flow one way, and that's how they implement the bits, 0 and 1, 0 and 1. Okay, so the transistors were used to make computers, and that marked the second generation of machines. From the IBM 7000, the DEC machines, right? DEC was very popular at that time because they produced this PDP-1 machines, right? And at that time, it was a very popular, robust mainframe kind of processor, okay, mainframe kind of computer. And they're used to do more complex calculations, okay? More complex than what ENIAC and the IS machine was able to do. Okay. So with the availability of more complex circuits and all that, so the language used to program these computers were now at a higher level now. Okay, they use higher level programming language. What's the difference between high level programming language and low level programming language? Now, high level programming language uses statements that are similar to how we talk. Okay, like natural language. So natural language is a very, very, very super duper high level language. Okay, a low level language is a language that the hardware will understand. Okay, very close to assembly language kind of programming. That means saying which data go where and do what calculation, exactly how to do. Very, very low level. Those are the more machine-friendly language, which the humans might not be able to understand so well. Okay, so that's the difference between high-level and low-level language. And of course, the more modern, the second-generation machine, they use a kind of system software already. Okay, maybe something similar to the operating system, a system kind of software. So generally, better performance, larger memory, larger size, and things like that. And they use transistors, of course. Okay, and of course with these transistors, there were from 18,000 vacuum tubes in the time of ENIAC. Now they use tens and hundreds and thousands of all these transistors, small components. Okay? So this is an example, the IBM 7000, and this is just like the front part, the console. The rest of the components are in cabinets. They use cabinets now, not entire walls of vacuum tubes, but now it's in the form of big cabinets. Big cabinets. The one on the right is the PDP-1, the first computer, or rather commercial computer by DEC. Right. So I'll just quickly show you a demo of PDP-1. I will unshare this and I will reshare the slide again to optimize for video. Just give me a minute. Okay, I'll show you a demo for PDP-1. Hopefully you can hear the audio as well.
Stereo, the alto, soprano, and the right speaker, tenor, and baritone on the left.
Stored in the tape, so you don't need to input this.
This is core memory.
The core memory,
yeah.
Okay.
So core memory is we're telling the magnetic donuts. And you set the value, turn the machine off, the memory's still there.
Okay.
So we just turn it back on, and it's sitting there, and back to let the switch go.
They just the core memory is 16 kilowatt.
We have 12 kilowords.
12 kilowatt. Okay.
Okay, so could you all hear and see the video just now? Okay, good. I forgot to introduce to you that at the beginning of the video, it shows the operator loading the punch cards. Okay, there were a lot of those cards kind of thing that has been fed, and then the program that was fed to the PDP-1 was to play some music. So if you notice, after the cards were being fed, there were this music. So it was actually programmed to make those sounds. Okay, and then the second half of the video showed a game being played. I think I saw on the chat they are playing this game called Space War or something like that. Yeah. So it was the program was loaded to also play some game and showed on the monitor. Okay. In the audio also you heard somebody talking about core memory. Now that core memory wasn't talking about what was shown on the screen. Okay, I think they were having a discussion about where the components were and where the core memory was stored and things like that. Okay, so you can see that video again via the link in eLearn. Okay, I've posted the link on eLearn. Later you can check. I'm not sure whether I've activated the link, but later I'll make that link available on eLearn for you to see that video again. Okay. All right, good. So as a rewind for this particular short section, what is a transistor? Again, can you please just quickly share in your chat, okay? What is a transistor? Okay, going through the chat box. Upgraded vacuum tube. Yes, that's true. It's an upgraded vacuum tube, but not a vacuum tube anymore. Okay. Switch or amplify electronic signals. All right. Replace the vacuum tubes. Okay. Second generation of computers. Yes. Replace vacuum tube. It's a micro switch. Okay. Yes, it's a very very small switch. As of course compared to the vacuum tubes lah. Amplify electronic signals. It represents a bit. It can be used to represent a bit, but not necessarily is a bit. Okay, so you can use transistors to implement bitwise calculations and all that. Okay, replacement of vacuum tubes, a solid state component. Yes. Upgrade of the vacuum tube is a switch. Semiconductor for electronic signals. Yes, that's true. Similar function like a vacuum tube, but much more compact and smaller. Yes. A transistor like vacuum tube. Yes. Second generation of bits. Yeah, something like that. Again, it's not bits per se, but it can be used to perform bitwise calculations. Right, good. Okay, so let's tie up that bit. I'm going to unshare this for a short while because it takes up resources to share the video. I'm going to revert back to the normal sharing. Wait a minute. Okay, good. Let's continue. Okay, so that was the second generation. Okay, second generation using transistors. Okay, using transistors, those small little components. The third generation uses integrated circuits. Okay, integrated circuits meaning again everything is then condensed into smaller size, and integrated meaning a few of these is then packaged into something very very small, like a board of some sort. Okay, and then this is based on microelectronics and uses gates, memory cells, as well as interconnections in order to implement the computer. Okay, now the gates here refers to, again, whether or not data is being allowed to flow through or not, and therefore that will then implement the various logical functions. Okay, so let's say, for example, one example of a gate is the AND gate. If, for example, 1 and 1, then only it becomes true. Okay, so that AND gate will allow certain inputs to be calculated or not exactly calculated, but decided what goes through. Okay, so if 1 and 1, then it becomes true, which means the output will be 1 as well. Okay, if it's 1 and 0, then the AND gate will decide, oh, it's a 0, it's a false. That kind of gate. Okay, we will discuss gates a little bit more in detail when we go to the topic on the digital logic. All right. Yes, the integrated circuits will then also be able to store bits of data, okay, in terms of ones and zeros, okay. So that is the some introduction. So remember the four functions again. You have data storage, data processing, data movement, and data control. Now all these functions can now be implemented on a semiconductor, okay, or on a single, on a single component, okay, and this is what we call a silicon wafer, okay, a wafer, a very very thin piece of material. So they manufacture it in terms of a large disk, okay, and each of those squares there refer to a chip, okay. So that means on the motherboard, you see that square processor chip there, that actually comes from one of these squares on that silicon wafer. Okay, so just on that one green square, you have the processor there with all the interconnections and all the very, 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 very small gates. So there are millions and millions of AND gates, OR gates, NAND gates, NOR gates, all the very, very different gates in order to perform all the various different logical functions, and they're all packaged onto a chip, okay, with some plastic casing and all the little legs for the connection for it to be mounted onto the motherboard. Okay, so basically it looks something like this. This is an example of the AMD 45 nanometer wafer. So if you notice, there are little squares on it, okay, so that refers to each chip, okay. Yeah. So again, this is a zoomed in image. So on that wafer you see the squares, and when you enlarge those squares, you will see what you will see the thing on the right, okay. So that is again a very, very zoomed in image. And of course, you can't see all the gates. Like, it's all very, 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 very microscopic. Okay, very, very microscopic. So, so we have seen from the vacuum tube we started off, okay, and all the way to different scales of integration. All right. So, from vacuum tube to transistors to small scale integration, then up to now, we have all the ultra large scale integration, which has millions and millions, hundreds of millions of devices on that chip. Okay, devices meaning all the various gates, okay, all the various gates, all the memory, memory storage, everything on that chip. Okay, so those are the levels of integration. Now, when we talk about this generation of computers with all the different levels of integration, we will see how many of these microscopic devices are then packed onto a single chip, right? Okay, like for example, the small scale integration, we're talking about just 100 devices on a chip, which means, let's say, 100 transistors on a chip, okay? Until that was back in 1965. Now, in the modern day computers, in from 1991, year 2000, now is 2020 already. There are hundreds and thousands or millions of all these components on a single chip. So there will be a progression on how many chips, or rather, how many components that we can pack on that single chip, and that brings us to Moore's law. Okay, now Moore's law, it says that the number of transistors that we can pack on a chip will double every year. Okay, the number of transistors that we can pack on a chip will double every year. Okay, that has been true for some time, but since the 1970s, the development has slowed down a little bit. Okay, so not necessarily every year, but it has doubled every 18 months to 2 years. Okay, so that is the progression that we have been making now, right? Now all those are happening. All this integration, the level of integration that has been happening, with the fact that the cost per chip is roughly the same. Okay, now although we are packing in more and more chips inside, it remains roughly as affordable as the earlier chips. Okay, that doesn't necessarily mean that you have doubled the number of chips, but you double the price also. Not necessarily so. Okay, so the cost remains very competitive as compared to the number of chips that we are packing inside, number of transistors or number of components that we are packing inside. Okay. Now, what happens when we pack more components into a single chip? Okay. Now, when we pack more components on a single chip, means that the components are closer together. Now, when they are closer together, means they are that the distance is very near, and therefore the signal that needs to travel is shorter. Okay, which means time is being saved. And time is being saved means better performance. Okay, so that is the idea behind making things smaller as well. So when it's smaller, the connections are shorter, the signals travel faster, and that leads to better performance. Okay. The smaller size also makes the overall packaging more flexible, which means you can take it anywhere, you put it anywhere, and so on and so forth. Okay. Power and cooling is also reduced. The components are nearer, so not much effort is needed to transmit the signal. Okay, and therefore less heat as well, right? So this is a diagram taken from I think World Data or something like that. It's also available on Wikipedia, by the way. So this is showing different processors. Okay, if you can see the later processors, you can see the see, my eyes are very poor already lah. The 72 core Xeon Phi processor, the AMD processor, Apple i12 Bionic. Okay, those are the upper end of the screen. So you can see this processor, see which year they belong to. Okay, so some of them are released in 2018. All right, and you see the number of transistors that are on that chip. Okay, so this is a logarithmic graph. So although the graph here is straight, but since it's a logarithmic graph, it actually means it's exponentially increasing year by year. Okay, so Moore's law is still holding today, but maybe at a different rate when he first suggested that particular law. All right. Okay. So as of 2015, Moore's law is 50 years old already. He first suggested this idea back in 1965. Okay, he was one of the founders of Intel. So until now, the law is still happening because it's still doubling every 18 months to 2 years and all that. So let's watch another video about him, talking about his law and things like that.
In 1965, when mainframe computers were just beginning to use integrated circuits, Gordon E. Moore published an article in Electronics magazine in which he predicted a very bright future for the computing industry. By tracking the evolution of integrated circuits to date, Moore predicted that the number of transistors in a dense integrated circuit would continue to grow exponentially. This observation became known as Moore's Law.
The message I was trying to get across was that integrated circuits were the road to less expensive electronics. It really evolved from being a measure of what goes on in the industry to something that more or less drives the industry.
If you compare the first microprocessor, Intel's 4004, to today's 14 nanometer processor, performance is now 3,500 times higher. Energy efficiency is improved 90,000 times, and the price per transistor has fallen by over 60,000 times. If automotive technology had progressed at the same rate, cars would go almost 300,000 miles per hour, get over 2 million miles per gallon, and cost only 4 cents.
No other technology that I can identify has made progress at that rate, nor has any had such a profound effect on the society throughout the world. And certainly in 1965, I would not have predicted the kind of products we make today. They're spectacular.
Moore's Law has driven Intel and the industry to make the impossible possible and to completely transform computing to create amazing experiences.
The potential is there for this change to continue, and I'm continually amazed at where it seems to be going. Just remember, whatever has been done can be outdone.
Okay, so that was the short video about Moore's Law. Let me get the slides back up again. Just give me a minute. Okay, so yeah, that was Moore's Law. And so let's talk a bit more about the more modern processors after we have, listened to the the third generation of computers with all these integrated circuits. So moving from that, all these are the more integrated circuits kind of computers already. So back in 1964, IBM had this 360 series, all right? And remember the architecture and the family, yeah? So something like that as well. Some of these IBM machines were not compatible, meaning that they were a totally different architecture. But later, when IBM had this, 7000 series and 360 series, some of these architectures remain the same for all the other IBM mainframe processors today. Okay, so later they implemented the family concept, so all these remain the same architecture. Okay, so the IBM 360 was the first planned family of computers. So they had similar instruction sets, similar operating systems, but they were all increasing in speeds, different number of ports, and so on and so forth. Okay, and of course, the more modern and the more high performance ones were more expensive, of course. Okay. Then other than the IBM machines, DEC, they also produced other more advanced PDP machines. So they had PDP-8, which is the first mini computer at that time. So at that time, 1960s, the mini skirt was very popular. Okay, the mini skirt was very popular. So for those computers that were made more compact and more small, so they coined the nickname mini computers. Okay, and basically all these smaller computers, they were not so heat generating anymore, so they do not need aircon rooms, and they were small enough to put on a bench or a table. Okay, and of course it's much cheaper compared to the early computers. $16,000. Okay, $16,000 to buy a computer today would be quite crazy. Okay. And then they also implemented certain architectural details that are quite similar to what we know today. Okay, like for example, the bus architecture. The bus architecture is used for some of the interconnections in the more modern computers as well. So, like in this case for PDP-8, the bus structure connects the CPU, the memory, and all the I/O modules. So, bus basically means there is a trunk, okay, like a main connection, and then all the components are then connected to that main trunk. So that is called the bus architecture. Okay. Then from the integrated circuit kind of computers come the more later generation ones that we are more we know today lah. So they use semiconductors. Okay, so these semiconductors were also used for memory as well. Okay, and this memory, of course, in the early stages they use ferromagnetic material, which means those materials are magnetic. So one example on the screen here is the core memory. Now we heard in the PDP-1 machine, the guys were talking about core memory. So yeah, they were referring to this kind of memory. Okay, it's on something like a chip, but then all the connections are made of magnetic material. Okay, and each of those cells refer to one bit lah. You can consider 1 bit. So if you have 8 of those little dots there, which means it's 8 bits, and so on and so on. Okay, and this one has 32 times 32.
Doctor, is this thing, this topic is about still in the history, not in the modern day, right?
I don't know. This is still in history. Memory we much later. Dr. Mami will cover after week 9 or week 10. Okay.
There's a lot of history here. You know, very, very, very big chunks of information in this history part.
Yeah. So this is just the first topic. This is a warm up. Don't worry. It's a warm up topic. So we just want to know what computer hardware is about, and then the next topic we will cover the binary number systems. Okay. So don't worry if you cannot remember any of these. These are some background information that we want to appreciate before we go into the details of the computer organization. Okay.
Thanks a lot.
All right. So in terms of the memory, again, the capacity more or less doubles every year as well. So like for example, a long time ago, having 2 meg RAM is very luxurious. So now 4 meg RAM, 8 meg RAM, it's very common. Why? Because when you buy one strip of RAM, the capacity is doubling. So instead of buying a small RAM, why not we buy a big RAM and it's still in the same space? Okay, so the capacity is also increasing every year. All right. So in the more modern memory, they don't use this magnetic core anymore. They don't use the magnetic core, but they use semiconductor etchings on a particular silicon wafer. Okay, so all these are not just microscopic; it's electron microscopic images of each memory cell, which means storing individual bits. Okay. Okay, so let's move into very quickly some of the later generation of processors. So again, in Moore's law's video just now, the narrator was mentioning about the 4004 processor. So that was Intel's first processor. Okay, and if you can see in the diagram also, that is the zoom in image. All right. Then it's then followed by the 8008 machine. Okay, and it's then 8-bit. The 4004 machine was a 4-bit machine only, a 4-bit machine. Then it moved into 8 bits. So you can imagine, if it's just a 4-bit machine, one word is only 4 bits, which means the largest number it can store for each word is 2 to the power of 4, okay? Which is only number 16. So if you want to store a larger number, then more of these words have to be combined together, right? So if you can imagine, a 4-bit machine is a bit complicated. Then with an 8-bit machine, the largest word you can store in one word is 2 to the power of 8, which is of course much larger than the 4004. Okay, and then in 1974, it's 8080, 8080, right? And then later, at the end of 1970s, came the so-called famous 8086. Okay, so that's why in our modern day, i5, i7 machines, that architecture is an X86 architecture, all right? And it was all based on this 8086 machine. And all the later architectures follow that same concept. Okay, so later, even in their 32-bit machine, in 1985, they have the 386. Okay, now back then it was called the 386 machine. It's still an X86 machine. Okay. As a conclusion, let's quickly talk about what computers did you first get acquainted with and what do you use it for? Okay. what computer did you first get acquainted with and what did you use it for? Now this one, I want to try a different kind of chat. Okay, don't just chat with everybody. I want you to do a pair chat. Okay, which means if you click on the two box, okay, that means the drop down box, you randomly choose somebody and you share these answers with them. Okay, and that person share their response with you. So that means if you receive a message, you reply with your own answer as well. Okay, and you yourself will have to do the same thing. You chat with somebody, and that person must chat back with you. Okay, so you might get multiple chatting, but at least one, isn't it? You share with that person, and that person must share with you. So if everybody do the same, everybody will get some form of message. Okay, so very, very quickly, in the chat box, chat with somebody privately. What computer did you first get acquainted with, and what did you use it for? Okay, very quickly, 1 minute.
Doctor,
Yes.
I'm sorry to bother, but can you explain me more about the architecture?
Architecture.
Yes.
Architecture meaning. Okay, early in the slide deck, architecture refers to things that are known to the programmer, like for example, the instruction sets and things like that. And normally, the architecture would then refer to a family of computers, which means those computers that are in the same family will share the same instruction set. Like for example, the i3, i5, i7, all these Intel processors, they share the same architecture.
What
means
does it mean by instruction set?
instruction set means, for example, multiplication, addition, subtraction, logical AND, logical OR. All these are instructions. So in an architecture which shares the same instruction set, that means the i5, i7, i3, they will know how to do multiplication, know how to do addition, know how to do logical AND, logical OR. This kind of things. Okay.
Let's say the instruction set we have for the i3 is 5,000 instruction. For the i7, it's the same 5,000.
Something like that. So they'll have similar instruction sets.
Similar instruction sets. Yeah, you mean Intel is different from AMD in the instruction sets?
No,
some differences.
In fact, like some AMD machines, they are also using an x86 kind of architecture as well. So that means that different programs can run on both the Intel machines and also the AMD machines because they borrow the same architecture. Okay. Now, having the instruction set that has nothing to do with the programming language. The programming language is one thing. The instruction set that is recognized by the processor is another thing. Okay.
So they are similar instruction set, and in number of bits.
The number of bits is also in the architecture as well. Yes.
And the input-output mechanism. So
correct. Yeah.
So we will say architecture of the Intel. The architecture of input and output is USB. Is USB port. That's what you refer to.
The USB port has to do with the input-output, but how does it handle the input-output is actually more important. Okay.
That's the architecture.
Yeah, that's the architecture.
How it's taking the data from the USB port and transmitting and moving it around the motherboard and the CPU and dealing with it in the processing unit.
Something like that. That means it must the instruction set must be able to know what to do with the data movement as well. Yeah.
Okay. The input and output mechanisms. Can you explain it more?
Okay, can I chat with you a little bit later after the lecture because I need to tie up some of these things. So can you please just stay online after the lecture has ended? Okay.
No problem.
Okay. All right. Regarding the chat, I hope you guys will keep the chat related to CST 131. Okay. please don't post messages about your games and things like that. All right. Okay, I hope you have done some individual chatting with regards to. Oh, I'm sorry. I think some of you may be using your computers to play games. Is it? Okay. I'm sorry about that. I thought that you all were chatting about, because earlier I saw some of you creating a room for your Among Us game and all that. So I thought you were still playing that kind of thing. Yeah, so I think, yeah, good. Some of you seem to some of you have used your first computer to play games. Okay, that is fine. Okay, sorry about that. I thought you were doing it for some other purpose. Okay, just to share also, as for me, my first computer that I was acquainted with is was the Apple II machine. Okay, Apple II machine. It has this 6502 chip, quite big chip. And I was using it among others to play games. I was doing a little bit of programming, and this was when I was, I think, uh, 10 years old, 11 years old, around that time. Okay. Yeah. So that was my first computer very, very long time ago. Okay. I think I will stop here. But before we go, I would like everyone to write a little reflection. Okay, I'm going to put the link on the chat box. Okay, I would like each of you to do a short reflection. Just a minute. Okay, a short reflection. If you can see the slides, from the lecture today, I learned. Okay, so go to the link in the chat box. It is also available on eLearn. You can click the link on eLearn for the lecture reflection. So very, very quick one. Maybe just 2 or 3 sentences. Just take half a minute or 1 minute. Just put in there. From the lecture today, I learned la 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 and so on. And after you have finished writing your reflection, that will be the end of the lecture, and you can log out. Okay. So thank you very much. I will see you on Tuesday. If you have any further questions, you can hang on behind. All right. Thank you. I will see you Tuesday. Okay, there's a question in the chat regarding tutorials. No, there's no tutorials. There's no tutorials next week. Tutorials will start on the 26th of October. Okay, the week of 26th of October. So if you are Group A or if you are Group B, your tutorial will start on the 26th. Okay, 26th of October. Yes, also from the chat, this refers only for CST 131. CST 131 tutorial starts 26th October. The other courses, the lecturers will inform you when tutorials are starting. Okay.
まさかあのマガザンがこんな形で崩壊するなんてね。
発着場の気空艇へ護送を開始します。逃亡者を出さないように。
Some of you are asking whether this particular chapter will come out as an exam question. That's a good question. Maybe it will, maybe it will not. Okay, because exam questions are not out yet, yeah, as it were. So anything can come out yet. So yeah, it depends. Okay, so but being a chapter as part of the syllabus, exam questions might come out from this chapter. Okay.
その中でもアシエ一家が一歩リードといったところか。
これは
金薬ヘブンと呼ぶにはまだ程遠いか。マガザンがヘブンの流通を締め付け始めた頃からアシエ一家は水面下で動き出した。
There's another request about making the PowerPoint slides available. Yes, I will make the PowerPoint slides available. Usually, I will release them before the lecture starts. I thought I have. Just give me a minute. I will just check.
涙ぐましい努力の結果、驚いたことにヘブンの調合を解析した。で、これがその試薬というわけだ。
Yes, the slides are already available. You can download from eLearn. Okay.
じきにヘブンの代用品になるに違いない。
Okay, do any of you have any anyone needing the attendance? Has all of you managed to anyone has not recorded your attendance? If you need attendance, if you need the link for the attendance, please indicate on the chat box, or you can unmute your mic and let me know.
まあ待て。まだあくまで試薬の段階だ。今すぐに市場に出回るわけじゃ。
Yes, doctor. You were talking about input and output and architecture.
それに、
and I unfortunately interrupted you.
Yes, so just give me a minute. I will just post up the QR code for those who haven't recorded. Okay. Sorry, you were asking about the I/O. Sorry.
Yes, I was talking about the architecture. The architecture. I need further explanation.
Regarding the input and output?
Architecture and the family. But firstly, the architecture.
Okay, I think at this stage, don't have to worry so much about what the architecture is. The basic definition for architecture is that the architecture refers to the characteristics of the computer that the user can know, or the user can that the user will know. Okay, because the user means maybe the programmer or the systems designer or whatever. So the architecture means characteristics that the user can see or the user can find out. So things like the instruction sets, the things like the number of bits. This one all of us know. Like for example, when you buy a Intel i3, i5, i7, you know that it has 32 bits or 64 bits, correct? If you go to the specifications, we can find out what are the instruction sets. Okay, so these things are made known to the user. Okay, but how the i3 or i5 implements certain instruction, like for example, in my lecture the other day, I said, okay, if you want to do multiplication, how do you do multiplication? Do you have a special component to do multiplication, or do you do multiplication by doing the addition a few times? Now, all these, the user don't need to know, right? So the organization is the things that the user don't have to know, like how a particular function or how a particular component does its job. The user does not need to know. So those are the organization. But if it's the architecture, the user will know. Like for example, the number of bits, what are the instruction sets, things like that. So that's the definition of architecture, and that is already enough for you to understand the basics. You don't have to go through in too much in detail, okay? But what were you asking about the I/O? I didn't quite understand what you want to know about the I/O.
I was referring I/O mechanisms. How does two devices share the architecture? Yeah, I need. How are they sharing it? That is the thing that I'm asking. You see, they share the same architecture. Is they share the same information, the number of bits. Like this laptop is 32 bits.
Okay.
Another, and it's Dell. HP produce a laptop and it's also 32 bits. That doesn't. This means that it has the same architecture, right?
Okay, so they have the same architecture.
Am I getting it right?
Yes, correct. So what has it got to do with the input-output? That part I don't understand.
Input-output mechanisms. You
how different computers talk to each other, or how the programs are, for example, let's say the same program, can I run it on the machine with one architecture and use the same program in another architecture? Is that what you mean?
No, I mean how it shares, what characteristics does the two devices share in the same architecture?
What the two? So okay, let's say for example, again, I will give you the same definition. Those two machines will have the same instruction set. The two machines will have the same number of bits. Things like that. So let's say for example, if you run a particular program, you run a particular program, and that program requires you to do some multiplication. Okay. So in that program, it says, X multiply Y, for example. Okay. So if I want to run it on one machine, that machine says that I have the instruction set for multiplication. And another computer, another architecture, the same architecture, it also has the same instruction set for multiplication. And so therefore that program can be run on these two computers because they have the same architecture. They have the same instruction set.
Great. That's all right. Very good. Let's go to the family.
Okay.
Family. Please explain to the family.
So family are different computers with the same architecture, but might have different specifications. Let's say one computer might have more RAM, for example, or another computer might have more. How should I say? Okay, maybe it's more RAM, and then maybe different circuits that maybe allows the computer to perform faster. Let's say for example, another machine maybe has more cores. Okay, let's say for example, i3, i5, i7, all of them same architecture and same family also. Okay, same family because they are all sharing the same architecture, but different specifications. i7 is maybe more cache, maybe more speed or whatever. But if you run the code, all of them can run the same code. So they are from the same family. different prices, different amount of cache memory, maybe different number of cores or whatever. So that one is the same family, okay? Same family, same architecture, but different implementation in terms of pricing, in terms of the memory,